and students, and as well as some other friends. Today, it's a great pleasure to have Professor Matti LASSAS from the University of Helsinki to give the departmental distinguished lecture. So Professor Matti LASSAS is a world top mathematician, and in particular, he is a leader in the field of inverse problems. And he is currently the academic professor of the University of Helsinki, and also the director of the Finnish Center of Excellence in Inverse Modeling and Imaging. Matti has made many fundamental and pioneering contributions to the field of inverse problems. And he also received numerous awards, distinguished awards, including the ICM invited the speaker in 2018. And also he is a member of the Finnish Academy of Science and Letters. And he is the inaugural winner of the Calderon Prize of the Inverse Problems International Association. Today he is going to talk about the inverse problem for nonlinear partial differential equations. And okay, Matti, I give the rest of the time to you.
Thank you very much for this invitation to give this talk. I wish very much that I could have been there in presence, because Hong Kong is one of my favorite places in the world. I hope that in the near future I can visit you again. But today we have to give this online talk. So I'm going to speak about inverse problems for different nonlinear partial differential equations. And in particular, I will speak why nonlinearity makes the problems easier. So why nonlinearity helps in imaging. So before going to nonlinear problems, I will first speak about linear problems when you have for the linear wave equation, like in this image, when you are interested of finding structures inside Earth. For instance, you are looking for gas or oil or some other structures. Typical measurements are that in the boundary of the domain, here on the surface of sea, you have some sources. These are so-called air guns that can produce huge acoustic signals. These sources produce a sound wave that propagates. It hits to the unknown structures, reflects, and returns back to the boundary, where there are microphones that record the sound. And from this type of measurements, where you control these sources, you would like to find out what are the structures that reflected the waves. So let me start with this linear inverse problem and formulate this first mathematically. So let us start in the case when M is a set in Rn, so 3 or 2-dimensional space typically. And let's assume now first for simplicity that this is compact set with smooth boundary. And we consider the wave equation. You denote the solution of wave equation. I use often the subscript F to indicate what is the source that produces the waves. So the model for this is that we have a wave equation with some unknown wave speed function, c of x, that we want to find out. At time t is equal to 0, the wave is 0. And on the boundary, the normal derivative of the wave, that is the Neumann data, this is given by function f. Physically speaking, this function f, this is the boundary source. So in this picture, f is the source produced by these air guns, and we can control it. Then we associate this wave speed c of x to Riemannian metric. The Riemannian metric corresponding to this particular model, where we have a scalar value speed. This is a metric tensor that is given by the matrix that is c of x to power -2 times diagonal matrix 1, 1, 1. So the identity matrix. And for this metric, it has a physical meaning because the distance with respect to this metric of 2 points x and y, this is the physical travel time from waves from when they travel from point x to y. So we measure now distances as time. So unit of distance is now seconds. How many seconds it takes for the wave, for instance here, to for instance reach the bottom and return back, or how much it takes time to propagate to the third layer. So in inverse problems, we assume that we know that there is a model that looks like this, but there are unknown coefficient functions. So the c of x, this is unknown function. And we want to determine it by using boundary measurements. And mathematically, the boundary measurements are modeled by the Neumann to Dirichlet map that map the Neumann data f to the Dirichlet data. So they map the source f to the boundary value of the solution. So we don't know what the system is. It has unknown coefficient functions, but we know what is the response that the system gives us. That if we put there a source f, we know what the response on the boundary is. And this is mathematical model of boundary measurements. So the boundary measurements, this mapping lambda, the Neumann to Dirichlet map, this is a linear map for linear equations that maps f to u of f. Now one often models this in a more geometrical way. Instead of speaking about scalar wave speed, one actually considers physical medium that has anisotropic wave speed. So it means that the wave speed depends on the direction where the waves are traveling. Waves can travel different way to up and down or in horizontal direction. And in this case, we model unknown object as a Riemannian manifold. So we have a manifold M, but typical example actually in physics is that M is the subset of Euclidean space. But there's a Riemannian metric, and then we consider the wave equation by using geometric operators like Laplace operator associated to Riemannian metric. It is given here. So this matrix G of x that is unknown, this determines the coefficients of this equation. And we want to find out what is this metric tensor. And again, this property that the Riemannian metric tensor corresponds to travel times of waves between 2 points, this is still true. And I will later go to details related to this equation. But again, the boundary measurements on the boundary of the manifold, they are modeled by the Neumann to Dirichlet map that maps the Neumann data of f, the normal derivative, to the boundary value of the solution. And we ask, does this map determine the Riemannian manifold and the metric of it? So the inverse problem that we study is the following. We assume that we have a Riemannian manifold with boundary. In this talk, you would think compact Riemannian manifold, but it can be also more complicated object. Then we assume that we know the boundary, and on the boundary, we have the source to solution map that maps the normal derivative to the boundary value of the solution. Reconstruction of a manifold actually means that we want to construct an equivalent Riemannian manifold. So we want to construct a manifold M prime G prime that is isometric to the original manifold. What this means in practical situations, if you think this again, this Earth imaging problem. In this case, the manifold M would be the half space. So the plane R2 multiplied with depth R plus. And we ask, can we reconstruct the metric tensor in local coordinates? So here we consider small sets where we have local coordinates. Can we reconstruct the image of metric tensor G in these coordinates? Or if we have a little bit more simpler model, we could ask, can we reconstruct the wave speed C of x? And we want to do the reconstruction only using the information on the boundary and this Neumann to Dirichlet. This is the inverse problem that we are studying. So, and these wave equations that I considered here, this and the earlier one, these are linear equations. Let me explain a bit the history. So now, from 80s, Belishev and Kurilev developed a so-called boundary control method that very much relies on the unique continuous results and equivalent controllability results by Daniel Tataru. This was studied in Euclidean space, and later it was generalized to inverse spectral problems that are equivalent to this inverse problem for wave equation on a manifold. Less than 10 years ago, with Bingham, Kurilev, and Siltanen, we developed an analogous method that is based on focusing of waves, and the focusing of waves is also essential here. But these problems are still these problems are under very active research. Very recently, in the last year, actually, Alexakis, Faiz Mohammadi, and Oksanen, they make a recent breakthrough when they allowed the coefficients of the equation also depend on time. And then they showed that one can determine the lower order terms in the wave equation when the metric depends on time and is close to Euclidean metric. So I want to point out that this sounds a little bit like Modius result, because one assumes that the metric is close to flat space. What makes it the true breakthrough? It is that all of these previous methods, they are used on Tataru's unique continuous result for wave equation, and this essentially requires that the metric is time independent. And this problem number 4, this uses a different technique. So this Tataru's unique continuous result, it has 2 negative features. First, it for instance restricts that the system may not have time-dependent coefficients, and second, it has relatively bad stability estimates. And today, my idea is to show that when we consider nonlinear equations, then we can use the nonlinearity as a tool to solve problems. For instance, we can solve problems with time-dependent coefficients. And this is a very curious thing. Usually in mathematics, nonlinear problems are much more difficult than linear problems. But in inverse problems, this is just in the opposite way. It turns out that nonlinear problems are easier, and we can solve for nonlinear equations, we can solve problems that are still open to linear problems. Okay. To go to nonlinear equations, I first start with some results for passive observations. And I'm going to speak about Lorentzian metric. And a typical example where one encounters Lorentzian metric is actually astronomy. Because if you look there, very long scales, very large scales, then the space-time is curved. So the gravitation makes the space-time curve, and there appears, for instance, gravitational lensing. So that when you have a massive object here, you have a source here, and you observe it here, then the light can have multiple paths between observers and source. You can get multiple images, like in this Einstein's cross, or you can get 3 Einstein rings, where a point-like object looks like an arc of ring. And in astronomy, this is, for instance, a problem where place where most of the observations are passive. We are not going to influence distant stars in any way. So we just observe light that comes from those. So what is this the idea of the passive measurements? So in astronomy is one problem. The other interesting problem are micro earthquakes, because after a large earthquake, there in same area there are lots of very small micro earthquakes, which means that you have lots of spontaneous earthquakes that just happen and you observe those. You could model those in this way, that you have some area that you want to image, and it has lots of point sources that can are active at some unknown time. And then you observe the waves in this blue region. So here, when one point source becomes active, like this becomes active here, it produces a wave, and when the wave arrives to the red region, then you observe it. and you observe when it travels through this blue region. So you don't know what's going on here in this area where the sources are. You only observe the waves far away in this blue region. Then you wait a little bit more, and some other point source become active, and it produces a wave. Now you started to observe it, and then you continue to observe it, and so on. And so this is very typical for these micro-earthquake problems. And because you cannot control the sources, you don't know when and you cannot change the times when they go off. This is called passive observations, because you only observe something, you don't control the sources. And in astronomy, you would think just that let's look sky, and they it looks very static for us. But if you look at it in long time, so in relativity, for instance, 1 year is extremely small time. So if you look stars several years, there are lots of varying stars where the brightness is changing, or you could even think like novas or supernovas that are very, very rapid from the cosmological scale. And then you can ask, by looking for sky, could you say how the space-time is curved? Okay, let's formulate these problems in a mathematical way. By the way, I forgot to say that if you have any questions, please don't hesitate to me and ask questions. So let us consider this type of relativistic inverse problem for passive observations. And let me explain this as a kind of like science fiction analogy. Let's assume that we do measurements close to Earth. So we consider space-time. So time here is the vertical direction, up and down, and space is horizontal direction. And in space-time, the road of Earth, this is a curve. So in time, when time propagates, the road of Earth draws a curve in space-time. So this black line here is the road of Earth, for instance. Then say that we do measurements in a neighborhood of Earth. There's a neighborhood V of Earth where we observe waves. And very far away, there are some point sources. For instance, there's in some distant galaxy, there's a supernova, a star explodes, and it sends a signal, cone of light. So it sends light to all directions. And in space-time, this means that there's a cone, light cone, that propagates to the future, and then we observe it here in ZV. So here's another picture. We do observations in this ZV here. Let's call it neighborhood of Earth. And then we have here a distant galaxy. And now we'll consider very long times. So there are lots of point sources. We assume that there are lots of point sources in this set U. And we are interested, what is the structure of space-time in this set U? And it is filled with point sources. And all of these point sources, they send light that is observed in this neighborhood V. This is the passive inverse problem. Let me now define this more rigorously. First, some definitions. Let M and G denote the Lorentzian manifold, so manifold M with Lawrencium metric. For instance, manifold could be the four-dimensional Euclidean space, so Minkowski space, with one time variable and three space variables. And the metric there, for instance, G is given by minus dt squared plus dx squared. Generally, this Lorentzian metric, at each point, it is a matrix, for instance, 4 times 4 matrix that has one negative eigenvalue and 3 positive eigenvalues in 4-dimensional space time. We denote by the geodesics by gamma x psi. This is the geodesic that starts from point x to direction psi. For instance, light rays are geodesics. And in Lorentzian geometry, the equations for geodesics are just the same as the equations in Riemannian geometry. So they are ordinary solutions of ordinary differential equations. And let me then recall a few other concepts of relativity. When we have a vector psi that has base point x, we say that it is time-like if the quadratic form determined by this Lawrencium metric, if psi's inner product with itself with respect to this indefinite metric g is negative. So this means that in this picture, if you have a vector that is based on origin, this point present, if the vector is pointing inside the light cone, then it is time-like. If this inner product is 0, this means that the vector is tangent to light cone. Then we say that the vector is light-like. And for instance, a time-like curve is a curve in space-time which velocity vector is always time-like. This corresponds to a particle that is moving with speed that is slower than speed of light. So a massive growth of massive particle. Then a little bit more somehow advanced definitions. When we have point x, when we have point p, like point present p, then j plus of p, this is the causal future of the point p. So here it is in the space time, it is everything that is inside the light cone, either on the light cone or inside it. This is the causal future. And similarly, j minus p, this is the causal past of point p. So in this picture, it's all points that are inside the past light cone. These are used in theory of Lorentzian geometry. And there's very important class of manifolds, so-called manifolds that are globally hyperbolic, that are those where we can solve wave equation. We say that the manifold is globally hyperbolic if two conditions are valid. First, there are no closed causal curves. What this means from practical terms, this means that we are considering a universe where we don't have time traveling. So it's pretty like physical assumption. Then the other assumption is that if I take any points P2 and P1 and P2, if P1 here is, for instance, here, and P2 is here, I take the future of P1 and I intersect with it with past of P2. These are called diamond sets because they look like diamonds. We require that these are compact to all points P1 and P2. So what this means? It means that you cannot make holes to spacetime because the spacetime is always assumed to be open Lorentzian manifold. If you would take, for instance, Euclidean space R4 and you would make there a hole. So you remove then a closed portion and you're left with some open set. Then this type of diamond set would not be compact. There would be boundary of the universe, basically. So this assumption basically says that there are no boundary of the universe that you could touch, or there are no singularities that are naked, that are not covered by horizons. So this is very similar requirement by saying that in Riemannian geometry the manifold is complete. And there's a theorem which says that if manifold is globally hyperbolic, then you can represent it as a product of time and space. And you can think that you have a manifold where you have a time varying metric, basically. So you split the manifold to time direction and space direction. But this metric is not product, it is metric is strongly time dependent. Okay, this is the class of manifolds that we are going to study. Then about the inverse problem, how to model measurements in this picture. So I recall that we think that we have neighborhood of Earth, we have some distant galaxy, and there are lots of point sources in this distant galaxy, like varying stars, or if you look very long time, it doesn't that you have there lots of novas, like sudden exposures. So the set V where we do measurements, we assume that it is a union of time-like curves, like in this picture. So let me again explain this in using science fiction or this kind of physical analogy. Let us consider neighborhood of Earth, and around Earth there are lots of satellites. So the satellites are moving along these red curves. These paths mu-a's are the roads of satellites in space-time. And the satellites are making observations in an open set close to Earth. And then we fix 2 points. We fix one satellite mu-a0, and we fix 2 points. Like here is P1 and here is P2. And then we assume that the area that we want to reconstruct, this distant galaxy U here, this is in the path of point P2, but not in path of P1. This basically ensures that the light from all points here is observed. So what are the observations? Observations are now observation time functions. They are the first times when we observe light coming from a point source on some path mu-a. So what this means? This means that we have a point source Q that sends light. We have a satellite mu-a on path mu-a that observes it. And this observation time function, this FQA, this is the first time when light from point Q is observed on the path that has number A. So this is the minimum of all parameters S, so that there is a future directed light like geodesic from Q to this point, mu A of S. And why we say here that it has first times? Let me go back to this the earlier picture. So here we had this this multipathing. There can be several light rays that arrive, and it was actually a very curious thing that actually this picture is taken from a very distant quasar, and there was some perturbations in this quasar. And when it is the brightness of these different images, they vary differently. And one notices then that the travel time along different paths in this picture, so what is the travel time of light along all these paths that you see here? It varied by several years. So actually, I think the time difference, maximum time difference between two, this very picture of one quasar, the difference of two paths was 4 years. So this is the small time scale now from the relativistic point of view. But let me go back to mathematics. Okay. So I recall I have an open set filled with paths, satellites. The satellites are observing light from point sources, and they record the first time when they observe light coming from a particular point source. Now with Kurelevan-Ullmann, we showed that this information is enough to determine structure of this unknown portion of the space-time U here. So indeed, that if we are on a globally hyperbolic Lorentzian manifold, where the dimension of space plus time is at least 2 plus 1, and we have this setting that we have observed things in a union of open set, that is union of paths. U is like in this picture here. So we are doing measurements in the neighborhood of Earth. Like I said, there's some distant galaxy. And if we are given the knowledge of the neighborhood of Earth and the metric in this neighborhood of Earth, and then we have some set U prime, that is dense subset of U. So we have a dense subset of this distant galaxy spacetime, and all points in U prime, they are some kind of point sources that produce light that is observed. So we observe the time observation. We have the knowledge of all observation time functions associated to point sources in a dense set in this region. Then we can reconstruct the topology of this portion U of spacetime in differentiable structure and also the conformal class of the metric. Today, I'm not going to speak about how this is proven, but this basically is similar to when you do triangularization on surface of Earth, when you are making like very precise maps, that you look at different marker points from different directions, and then you are matching your observations to make a map on the surface of Earth. But the moral of this is that that you want to, if you observe light from point sources, then you can reconstruct the structure of space-time in this region. And the metric up to so you reconstruct conformal class of the metric. This means reconstruct the metric up to a scalar function. Let us now use this to inverse problems for nonlinear equations. Let me first explain the model. Now we consider a globally hyperbolic Lorentzian manifold that can be split as a product of time axis and space. And this is at least dimension 1 plus 2 or more. Then we consider a simple nonlinear equation. The simple nonlinear equation here is that we have a linear wave operator, formula of the linear wave operator corresponding to Lorentzian metric. G is here. This is indeed a wave operator because the metric is now such that it has one. The matrix G has one negative eigenvalue, other eigenvalues are positive. So this is like a hyperbolic operator. So we have linear wave operator operating to U, and then U to power M, where M is not 1. And then we are, so this is a linear wave operator plus a simple nonlinear term. In an alternative model, if you would not forget all the geometry and wouldn't like to speak about metric tensors, would be that you would have a wave equation, wave operator here, minus the dt squared of u minus wave speed times Laplacian in the space variables of u, where the wave speed depends on space and time, plus then some nonlinear term. This corresponds this type of Lorentzian metric. So this is the model that we consider. And we put there a source that we can control. We have a source f that we control. I point out here that I use this differential geometric notation where the variables have upper indices. And also in Lorentzian geometry, x0, this is the time coordinate, and the rest are space coordinates. Okay. So with Kurylev and Ullmann, and later somehow modified this result with Ullmann and Wang, we showed that in 4-dimensional space-time, with the following result is true. Let me again now explain this as a science fiction analogy. Let's assume that we have a spaceship mu that wants to observe space-time close to it. So the road of the spaceship is mu in space-time. Then I take 2 points, P1 and P2, on the road of this P1. So P1 is spaceship at some past time, and P2 is spaceship at some future time. Everything here is now in space-time. And then we assume that we can do measurements in a neighborhood V of this path mu. So the spaceship can change things close to it. This means that the spaceship can measure the short solution map for nonlinear wave equation. And here I use the result is quadratic nonlinearity. So when f is a source that is supported in this set V here, this source produces some wave that propagates in space-time. Some of this wave can return back to V, and we observe it here. So we have sources in small neighborhood V, and we observe waves only in this V. And the outside is unknown. This result says that if we know V and we know this short solution map, then we can reconstruct space-time in this diamond. Diamond W, that is the future of P1 intersected with P2. So why this is very natural domain? This is the area where waves can propagate and return back to carry information, what they experienced. So waves need to propagate some portion of space-time and return back where we can observe those. So indeed, the measurements that the spaceship does, these active measurements by varying f, This determines the space-time in this large causal diamond, and also reconstructs the metric on this set, so up to change of coordinates. And this is also done for using Dirichlet-to-Neumann maps for boundary problems recently in last year. So what is the idea here? The idea is that we are going to use interaction of waves. So here is a video where there are 4 plane waves that are propagating. So when these waves propagate, they start to interact, and when they bounce all together, like this is the moment now when all these waves arrive at the same point, then they produce a point source that we call artificial microlocal point source, and this point source produces a wave that goes to all directions. So what this means? Interactions of waves, they can produce point sources into unknown region. So this now changes the inverse problem for active measurements. It changes it to a passive inverse problem, where we assume that there are lots of point sources in space-time. We observe light coming from those point sources, and we already know that the passive observations from point sources, they determine the conformal class of the metric. So conformal class means up to scalar multiplication. So basically, we use this interaction of waves to produce point sources. We fill the unknown portion of the space-time with artificial point sources, and then light from those determine the metric. Let me explain the proof, ideas of proof. And for that, let us consider 4th order nonlinearity, u to power 4, and we have now 1 plus 3-dimensional space-time. So we have flat Minkowski space. There we have just the standard Euclidean wave equation plus 4th order nonlinearity. And now I consider solutions that depend on parameters epsilon1, epsilon2, epsilon3, epsilon4 that I denote by epsilon vector. And I'm considering small values of these parameters. Let us assume that when epsilons are 0, then the wave is 0. And then we consider derivatives. The first derivatives are so-called linearized waves, and they satisfy a linear wave equation. But when I differentiate this equation 4 times, with respect to different epsilon parameters, I compute the epsilon1 derivative, epsilon2, epsilon3, epsilon4 derivative of these solutions. Then this 4th order term here, this gives some contribution. And this 4th order derivative of this wave, this satisfies the wave equation with the source term. And the source is a constant times a product of u1, u2, u3, u4. So we call this artificial source. Why is that? Because the equation has no sources. The equation has nonlinear terms, but the nonlinear terms produce something that looks like sources. So there are no physical sources, but the interaction produces like secondary sources. Those we call artificial sources. So why these products are interesting? Let us consider the model where we collide 4 plane waves. So let u1, for instance, be the delta wave. So this here is Dirac delta distribution of t time minus the first space variable, the first coordinate. We use the coordinates where the coordinates of space-time are t, and then that is for time, and then y1, y2, y3 to space coordinates. So we have here 3 delta waves like this, and then we also have a 4th wave that we have just are coming from like a slanted direction. Now, when we multiply these functions together, what happens? Each of these waves is supported on a hyperplane in space-time. So the product is supported in an intersection of 4 hyperplanes. So we have 4-dimensional space-time. We take intersection of 4 hyperplanes. Their intersection is a single point. This explains why this product of 4 delta waves produces the delta distribution. And this means now that this for interaction of the waves, this produces, this satisfies the wave equation with artificial source that is constant times this product of four linearized waves, that is delta distribution. So S basically is artificial point source. Okay, what's going on recently? Recently we have somehow also studied the both cases when the set where we produce the waves, so where the sources F are supported, and the area where we observe the waves, they are disjoint. And in this case, in this kind of geometrical picture, one can reconstruct the space-time in this type of diamond set that is such that the waves can start from the causal, it is union of four causal paths that start from this omega in, travel anywhere and return to omega out. And also we are able to somehow consider much more complicated equations. For instance, here's a quasi-linear equation with the Lawrencium metric that depends on the solution. And one has to require here that this equation is really nonlinear, so that, for instance, that here we that the second derivative of g is non-zero. So if we, in this kind of geometrical picture, you have sources in omega in, you have observed waves in omega out, you assume that you have the source to solution map that maps the source to values of solution in this omega out, then this determines the conformal class of the metric tensor, this g when the value of the wave is zero. So why this conformal class means up to a scalar multiplication. Why this is very natural? This is very natural because in the region, for in this omega out area, or actually outside the omega in, f is zero. So then if you take this equation, you multiply g by a scalar function, this equation is not changed. So conformal class is best that you can try to reconstruct. Here the idea is that one uses actually third order interaction of waves. So what this means? This means that if you consider now different model equation, wave equation, plus u to power 3, again I consider different the solutions depending on different parameters, epsilon 1, epsilon 2, epsilon 3. When I take the derivatives, the first derivatives are linearized waves, they satisfy the linear wave equation. And then the third order derivative is now a solution of wave equation with artificial source term S, where S is product of three waves. So what is the product of three waves? For instance, if we again have delta waves, we have delta waves that are supported on a hyperplanes in space-time, like here. When I multiply those together, I obtain this function that is supported on the intersection of three hyperplanes in space-time. I have four-dimensional space-time, and I intersect there three hyperplanes. Dimension count says that the intersection is a line. So this product here is delta distribution on a line. And what is the what actually means that we have some object that is supported? We have a source that is supported on a line in space-time. This actually is the same as say that we have a point source that is moving. So if you have a point that moves in space-time, its world curve draws a curve. So actually a curve in space-time is a path of a moving point. So physically speaking, this three interaction of waves, this is produced by a moving point source. And this point source can move with the speed that is like faster than speed of light, or even infinitely fast. In this very picture, when we have these particular waves, actually the point source is moving infinitely fast. So what it means, like in this picture, you have 3 planes that are propagating in space-time. Then they all collide along a line. Then in this line, you have a source, and this produces a conic wave that starts to propagate in these different directions. And let me show other example. Now, if you have 3 planes that have are slightly differently oriented, when they start to propagate, then they intersect in such a way that the intersection in space-time is a line. The line corresponds to very fastly moving point source, and this produces a piece of conic wave. So there's this kind of ring-like wave that starts to propagate. And what one can show that if one slightly varies this interacting, that the planes, the directions of the planes. So you slightly vary the directions where the planes come in. Then the orientation of the ring changes, and you can rotate the ring and so on. So you can send this type of ring-like wave to the almost to any direction. And these can now this kind of a little bit more complicated sources that correspond lines in space-time. You can use those to replace the point sources. This is actually important because mathematical analysis is much more easier to 3 interactions than for 4 interactions. Even though the geometry looks a little bit more complicated, mathematically speaking, the analysis of this type of interaction of singularities are much simpler in this case. So actually, this kind of principle that the interaction of nonlinear interaction of waves or solutions in general, that can be used as a tool in imaging. This has been now used in recent years to vary those problems for inverse boundary value problems, for scattering problems, for elastic systems. Actually, in Hong Kong, there's like also remarkable progress on parabolic equations. Of course, not all of these authors are from Hong Kong, like Yi-Xuan Lin, Hongzhu Liu, Xu Lin, Chen Chang. They showed that for parabolic equations, a remarkable result that using this kind of interaction of nonlinear interaction of solutions can be used to reconstruct both the system and the unknown initial state. And then also there are results to Boltzmann equations, Schrödinger equations, Yang-Mills equations, and to Einstein equations. And in all of these equations, it turns out that the nonlinearity helps solving the inverse problem. So the nonlinear terms can be used as a tool to do imaging. Let me say a few words about inverse problems for elliptic equations. For instance, there are results. There are quite many authors working on this, but let me explain our results with Li-Matan, Yi-Xuan Lin, and Salo, which is that the following elliptic problem. Let us consider domain omega in Rn that is in some bounded domain, and the geometry is the following. We have a large domain omega that is filled with 2 unknown things. One is that there's a cavity, a hole, D, so it has these holes, D's here. The union of these 3 holes is D. And then there's also an unknown term that is q of x times n u to power m. And we assume that this m is at least 2. We assume that we can control the boundary value f here in the outer surface. But on this internal boundary, in the cavities, we just know that the boundary value is 0. Then we define the boundary value map on the boundary of this outer boundary of d omega that maps this boundary value f to the normal derivative of the solution on this outer boundary. And it turns out that this map determines uniquely this set D, so the internal holes, and the nonlinear coefficient. If this power m would be 1, so we would have a linear equation, then this is one of these kind of big problems in inverse problems, how you could reconstruct things, Schrödinger operator, by using like partial measurements. It is open problem. But when you add here this nonlinearity, then you can reconstruct here both the cavities and the coefficients of the equation. So again, for elliptic equations, the nonlinear interaction helps. Let me skip some other result. I just show very quickly what is the idea in this kind of approaches. In general, when you consider the higher order Fessy derivatives of your boundary operators, they give you products of unknown terms and solutions of linearized equations. And these linearized equations are just now basically harmonic functions. And in inverse problems, there has been lots of work originally by Calderon, then Sylvester and Ullmann, and recently by Guillermo and Zhou, who analyzed when the products of harmonic functions, when the products of two harmonic functions are dense, for instance, in L2 or L1. And these kind of results can be used to solve the problems. So roughly speaking, this means that to study nonlinear equations, you only have to study linearized equations with known coefficients. So nonlinearity helps a lot also in study of elliptic equations. And I finish here. Thank you very much for your attention. Thank you very much.
Thank you, Matti, for the wonderful talk. Okay, now it's time for questions or comments. You know, any comments, questions from our audience? All right. We got a very quiet audience. Okay, this is usually the case for the online talk. Okay, maybe I can start a few questions, Matti. Okay,
please.
It's really inspiring. So my first question is about the space-time structure determination. So for that part, I think the first is that you can determine the space-time structure in the subset U in the what you just said, this galaxy-like, that's the space-time. So for that one, it seems that U also depends. This set U depends on the source place. Depends on the source. The unknown, the passive source. So,
yes, so let you mean let me just go. You mean
the result? Yes, yeah, yes. The result is. Oh no! The previous one, I say the previous slide.
So this or
no okay the passive measurement, yes.
Yeah.
So basically you can determine the space-time structure in the subset U in the whole space, the whole universe. So this U actually depends on the source location, right? Depends on your source. Even they are unknown, but they depends on the source.
Yes. So we assume that there is some set that contains lots of these point sources. So we could think that we have some point sources, and then we define that U is the set that contains these point sources.
Oh, yeah. My question is that how big can it be? Could it be very big? I mean, compared to those sources, you know.
Yes. So at this moment, unfortunately, what we so this is uniqueness results. We don't have yet stability results. One unfortunate feature that we still are studying is that what happens if the set U it is infinite, that it goes all the way to the past.
Okay,
And
that's
this one, we don't need, we don't know like what happens in this case. That if we would like image everything up until the Big Bang, that we cannot do yet. So we have to have some like localized like area in space-time that does not last infinitely long. This is a really, but usually in inverse problems we always start that we have some say unknown object in a compact set, and later we are studying like scattering problems or what happens in infinite space.
Okay.
So there are lots of open questions actually also in this geometric problem.
Okay, that's very nice. Definitely, I'm just curious about this. So another thing is that also, so actually it depends on the metric inside this set U, but this metric is also time independent actually, right?
So this here, sorry, the metric here, this is a general Lorentzian metric, so it can depend on all coordinates. So yes, okay, I have to say, unfortunately, yes, this Lorentzian conventions is that when one speaks about, like when one denotes x, the x is denote the coordinate point of space-time. So it has both time coordinate and space coordinates. This is a little bit unfortunate, but because the mixture of there's no global time in Lorentzian geometry, then for instance in Minkowski space we can split the space in many different ways to space and time. So there is no canonical time. There are different time functions associated to each observer. So that's why there's no natural like decomposition of time and space. There are many of them, but they all depend. They're relative of the person who makes observations.
Okay, thank you. So my last question is, for the last part, for the nonlinear elliptic PDEs, that's really interesting. Actually, indeed, it's an open problem, right? Yes. So it's kind of it looks like to me it's kind of like a regularization. The nonlinear term. It's kind of a linearization. You produce more information. That's going to help you to solve this open problem. But my question is that definitely you can use this physical interference to introduce force this inject this nonlinearity to your physical system to regularize your linear system. Yes. So my question is that can we do this non-physical way, artificial, not necessarily use this physical apparatus or physical interference to produce this kind of linearization? Is that possible? What's your opinion?
So if you, I think even also you have studied. If I manage to correctly, you are asking that is this non-linearity? It is a kind of like regularization.
Yes.
I know that, for instance, you have been studying this type of problems when you put to the medium some non-linear nanoparticles.
Yes.
Imaging. And so, but maybe the cool question is, could you do this just mathematically? Use this as a kind of regularization technique. That is a good idea. I don't know about that. Okay. One very nice feature actually of this now new trend of inverse problems to study nonlinear equations is that this is really fresh field we researchers in inverse problems, we have mostly studied linear problems. So all collaboration with people who study nonlinear equations are now very welcome because they are experts on the field that we now need to learn, because we somehow see that there are lots of possibilities to apply all type of nonlinear analysis to inverse problems.
Yes. Yeah, you are the pioneering figure in this field. Okay, so that's all my questions. So let's any other questions or comments from the audience? Okay. So if no more questions, let's thank the Professor Matti LASSAS for the inspiring talk again. Thank you, Matti.
And thank you very much for your interest and your invitation. Thank you.
Okay, so Matti, you must feel tired, so you can take a break. And we stay in touch. No, especially there will be a a certain amount of honorarium provided to you from our department. So the secretary gonna in touch with you very soon. Okay.
And thank you very much. And I hope very much that I have possibility to travel in near future to Hong Kong to meet many of you.
Oh, absolutely. You're always welcome to visit us again. Okay, yeah. Matti. So take care and stay healthy. Okay.
Yes. Thank you very much.
Yes. Okay. Thank you. Bye bye.